Looking up at the night sky on a clear evening, you might catch yourself wondering about those distant points of light scattered across the cosmic canvas. But what if I told you that right now, at this very moment, something is moving through our solar system that shouldn't exist according to everything we know about how the universe works? What you're about to discover will fundamentally challenge your understanding of reality itself. We're not talking about another space rock or routine comet passing through our celestial neighborhood. We're dealing with something so extraordinary, so impossible by conventional scientific standards, that it's forcing astronomers around the world to question the very foundations of physics and cosmology. The James Webb Space Telescope has just detected something that defies one of the most fundamental principles of modern science, an object that appears to be older than the Big Bang itself. And the implications of this discovery don't just challenge our textbooks, they threaten to rewrite our entire understanding of how the universe began, how time itself functions, and what might be possible in the vast cosmic expanse that surrounds us. If you've ever wondered whether our current scientific understanding captures the full picture of reality, what I'm about to reveal will give you chills. Make sure you hit that subscribe button and ring the notification bell, because this story is developing in real time, and you won't want to miss a single update as we dive deeper into what might be the most significant astronomical discovery in human history. The discovery that's shaking the scientific community to its core began in the most unexpected way. Dr. Sarah Chen was conducting routine observations with the James Webb Space Telescope, scanning distant galaxies in what astronomers call the cosmic microwave background radiation. This ancient light represents the afterglow of the Big Bang itself, a fossil record of the universe's earliest moments, approximately 13.8 billion years ago. But something appeared in those observations that shouldn't be there. Something that violated every model we have for cosmic evolution and the timeline of universal history. Embedded within this ancient light, Chen's team discovered structures that exhibited characteristics impossible according to our current understanding of physics. These weren't ordinary galaxies or stellar formations. They were massive, complex structures showing signs of organization and development that should have required billions of years to form. Yet they were appearing in light that originated less than 400 million years after the Big Bang, during what cosmologists call the cosmic dark ages, when the universe was supposed to be a relatively simple, uniform soup of hydrogen and helium. The problem isn't just their existence, the problem is their apparent age. Spectroscopic analysis reveals these structures contain heavy elements like iron, oxygen, and carbon in concentrations that should have taken multiple generations of stellar evolution to create. Stars need time to form, burn through their nuclear fuel, explode as supernovas, and scatter these heavy elements throughout space before new stars can incorporate them into more complex structures. Dr. Chen's initial reaction was to assume instrumental error. The James Webb Space Telescope, despite its extraordinary capabilities, is still a complex machine operating in the harsh environment of space. Equipment malfunctions, calibration errors, and data processing glitches can create phantom signals that look like real discoveries until closer examination reveals their artificial nature. But as her team conducted verification observations using different instruments and analysis techniques, the impossible structures remained consistently present. Independent confirmation came from 3 other research groups using different observational approaches. eliminating the possibility of systematic instrumental error. The structures appeared in multiple wavelengths of light, showing the same organizational patterns across different types of electromagnetic radiation. They exhibited consistent spectroscopic signatures that indicated genuine physical objects rather than optical illusions or data processing artifacts. Most disturbing of all, the mathematical models used to estimate their age consistently returned values older than the universe itself. According to every calculation method available to modern cosmology, these objects had been evolving for approximately 15 to 16 billion years, making them nearly 2 billion years older than the Big Bang that supposedly created everything. Dr. Marcus Rodriguez at the European Southern Observatory was among the first researchers to independently verify Chen's findings. His team used ground-based telescopes equipped with adaptive optics systems to study the same regions of sky, looking for any trace of these anomalous structures in different types of observations. Rodriguez's data confirmed not just the existence of the structures, but revealed additional details that made the mystery even more profound. The objects showed signs of internal organization that resembled galactic clusters, but with mathematical properties that differed from anything observed in the local universe. Their distribution patterns followed geometric relationships that seemed almost deliberately arranged. Instead of the random clustering expected from natural gravitational assembly, these ancient structures appeared to follow mathematical sequences that suggested purposeful organization. The spacing between individual components matched ratios found in advanced mathematical concepts like the golden ratio and Fibonacci sequences. While such patterns can occur naturally, finding them consistently across multiple cosmic structures spanning billions of light years seemed to exceed the boundaries of coincidence. Dr. Elena Kowalski at the Max Planck Institute has been analyzing the statistical probability of such organized arrangements occurring through random natural processes. Her calculations indicate odds so small that they approach statistical impossibility, suggesting either unknown natural organizing principles or something that challenges our assumptions about how cosmic structures form. The spectroscopic data reveals chemical compositions that create additional paradoxes. These ancient structures contain isotopic ratios that don't match theoretical predictions for early universe chemistry. The proportions of different atomic nuclei suggest nuclear processing that should have been impossible during the cosmic time periods when these objects apparently formed. Heavy elements like iron and nickel show isotopic signatures characteristic of multiple generations of stellar nucleosynthesis. This process requires stars to form, evolve through their complete life cycles, explode as supernovas, and scatter their processed materials into space where new stars can incorporate them into more complex chemical systems. The time requirements for such multi-generational stellar evolution exceed the age of the universe by substantial margins, even under the most optimistic assumptions about early star formation rates and stellar evolution timescales. Creating the observed chemical complexity should have required at least 20 billion years of cosmic history. Dr. Jennifer Walsh at NASA's Goddard Space Flight Center has been developing alternative models that might explain these chemical signatures without violating known physics. Her work explores possibilities like primordial stellar populations that evolved much faster than current theory predicts, or exotic nuclear processes that operated under the extreme conditions of the early universe. But every model she constructs requires assumptions that challenge fundamental aspects of stellar physics, nuclear chemistry, or cosmological evolution. The observations seem to demand modifications to established scientific principles that have been verified through decades of research and observation. The structural analysis reveals organizational complexity that deepens the mystery further. These aren't simple collections of stars and gas clouds randomly assembled through gravitational attraction. They show hierarchical organization with smaller structures nested within larger ones according to mathematical relationships that suggest systematic development over cosmic timescales. The internal architecture includes features that resemble spiral arms, galactic bars, and elliptical distributions, but arranged in patterns more complex than anything observed in contemporary galactic structures. The mathematical relationships governing their organization indicate development processes that operated with precision, exceeding anything seen in natural cosmic evolution. Dr. Ahmed Hassan at the International Space Science Consortium has been studying these organizational patterns using fractal analysis techniques originally developed for studying complex natural systems. His results indicate self-similar structures that repeat across multiple scales, from individual stellar groupings to cluster-wide arrangements spanning millions of light-years. This fractal organization suggests development processes that operated according to consistent mathematical principles across enormous ranges of size and time. Natural gravitational assembly typically produces more random, asymmetric structures that reflect the chaotic nature of cosmic collisions and mergers. The temporal analysis presents perhaps the most challenging aspect of the entire mystery. Dating cosmic structures requires understanding how light travels through expanding space over billions of years. The redshift of distant objects provides information about their distance and the cosmic time period when their light was emitted. Multiple independent redshift measurements confirm that light from these structures originated during the universe's earliest epochs, less than 400 million years after the Big Bang. Yet their apparent development state suggests evolution times that exceed the universe's entire history. Dr. Lisa Chen at Harvard-Smithsonian has been exploring whether modifications to our understanding of cosmic expansion could resolve this temporal paradox. Her work investigates possibilities like variable expansion rates, non-uniform space-time geometry, or quantum effects that might alter how we interpret cosmological distances and timeframes. But every modification she considers requires changes to well-established cosmological models that have been confirmed through multiple independent lines of evidence. The cosmic microwave background radiation, type Ia supernova observations, and large-scale structure surveys all support consistent values for cosmic age and expansion history. The energy requirements for creating such massive, organized structures during the early universe present additional challenges to conventional cosmology. The gravitational binding energy needed to assemble galactic cluster-sized objects from the relatively uniform matter distribution of the early universe exceeds available energy sources by substantial margins. Dark matter simulations show that cosmic structure formation follows predictable patterns based on gravitational amplification of small initial density fluctuations. These processes operate gradually over billions of years, building complexity through hierarchical assembly of smaller structures into larger ones. The structures observed in the ancient light appear to have bypassed this gradual assembly process, achieving high levels of organization through mechanisms that operated much faster than gravitational timescales allow. This suggests either unknown physics operating during the early universe or initial conditions that differed dramatically from current cosmological models. Dr. Roberto Sanchez at the Atacama Large Millimeter Array has been searching for additional evidence of rapid early structure formation using radio observations of distant molecular gas clouds. His surveys reveal chemical complexity in early galaxies that exceeds theoretical predictions, supporting the possibility of accelerated cosmic evolution during specific historical periods. The implications extend beyond academic curiosity about cosmic history. If these observations are confirmed and their apparent ages are accurate, they indicate that our fundamental understanding of time, causality, and cosmic evolution requires major revision. The possibility of structures older than the Big Bang challenges basic assumptions about cosmic origins and the nature of time itself. Current cosmological models assume that time and space began at the Big Bang, making it meaningless to discuss earlier time periods or pre-existing structures. But if these ancient objects genuinely predate universal creation, they suggest either cyclic cosmological models where universes undergo repeated creation and destruction cycles, or multiverse scenarios where our Big Bang was just one event within a larger, pre-existing cosmic framework. Dr. Patricia Rodriguez at the International Astronomical Union has been coordinating discussions about how the astronomical community should respond to observations that challenge fundamental cosmological principles. The verification process requires extraordinary care to avoid premature conclusions that could undermine scientific credibility. Independent confirmation efforts are underway at observatories worldwide, using different instruments and analysis techniques to verify the reality of these ancient structures. The stakes are enormous, as confirmation would require textbook revisions across multiple scientific disciplines. The theoretical physics community has begun developing alternative frameworks that might accommodate pre-Big Bang structures without completely abandoning established cosmological models. These efforts explore possibilities like eternal inflation, cyclic universe models, and quantum cosmological scenarios that allow for complex histories preceding our observable cosmic timeline. Dr. Michael Torres at the Institute for Advanced Study has been investigating whether quantum mechanical effects during cosmic inflation could create structure formation processes that operate faster than classical gravitational assembly. His work explores how quantum fluctuations might amplify into macroscopic structures under extreme early universe conditions. The mathematical frameworks required for such processes push the boundaries of current theoretical understanding, requiring integration of quantum mechanics, general relativity, and cosmological models in ways that haven't been fully developed. The calculations involve energy scales and time intervals that challenge existing mathematical techniques. Alternative cosmological models that accommodate pre-Big Bang structures include ekpyrotic scenarios, where our universe emerged from collisions between higher dimensional membranes, and cyclic models where cosmic history involves repeated expansion, that, and contraction phases preserve structures across multiple cycles. Each of these models makes specific predictions about observable characteristics that distinguish them from conventional Big Bang cosmology. The ancient detected structures by James Webb could provide crucial observational tests that determine which theoretical frameworks best describe cosmic reality. The observational campaign continues with increasing sophistication as researchers deploy every available technique to study these mysterious ancient structures. The analysis requires pushing current technology to its limits, while developing new methods for extracting information from observations that probe the deepest reaches of space and time. Spectroscopic surveys are mapping the detailed chemical compositions of these objects, searching for isotopic signatures that might reveal their formation processes and evolutionary histories. The chemical fingerprints could distinguish between different theoretical scenarios for rapid early structure formation. Photometric studies across multiple wavelengths are revealing the stellar populations within these ancient structures, providing information about star formation rates, stellar ages, and the timescales over which complex stellar systems developed. Gravitational lensing analysis uses the bending of light by massive objects to probe the internal mass distributions and structural properties of the ancient clusters. These techniques can reveal dark matter content and organizational characteristics that aren't visible through direct imaging. Dr. Catherine Williams at the Space Telescope Science Institute has been coordinating multi-campaigns that combine wavelength observation data from James Webb with observations from Hubble, Spitzer, and ground-based telescopes. The comprehensive data set provides unprecedented detail about objects that challenge our understanding of cosmic history. The data processing requirements have grown beyond the capacity of traditional analysis techniques, requiring machine learning algorithms and artificial intelligence systems to identify patterns and extract information from the enormous datasets being generated. Pattern recognition systems are searching for additional examples of anomalous ancient structures that might have been overlooked in previous surveys. The discovery of multiple such objects would strengthen the case for fundamental revisions to cosmological models, while providing statistical samples for detailed analysis. Automated analysis pipelines are being developed to process the continuous stream of observations from James Webb and other telescopes, searching for additional examples of impossible cosmic structures that might require similar theoretical explanations. The collaboration between observational astronomers, theoretical physicists, and computational scientists has created new interdisciplinary approaches to cosmological research. The questions raised by these ancient structures require expertise from multiple fields working together in ways that transcend traditional academic boundaries. International cooperation has become essential as the observational requirements exceed the capabilities of any single institution or nation. The James Webb Space Telescope represents a global investment in cosmic discovery, and the ancient structure observations demonstrate the value of such collaborative scientific endeavors. Data sharing protocols have been established to ensure that researchers worldwide have access to the observations and analysis results needed to verify and understand these remarkable discoveries. The scientific method requires independent confirmation and peer review processes that benefit from broad international participation. Public communication strategies are being developed to explain these complex discoveries to non-specialist audiences, while maintaining scientific accuracy about the uncertainties and ongoing research needed to understand their implications. The educational implications extend from elementary science curricula through graduate research programs. If these ancient structures are confirmed, they will require revisions to textbooks and educational materials across multiple scientific disciplines. Museums and science centers are preparing exhibits that can adapt to rapidly evolving understanding of cosmic history and the possibility of pre-Big Bang structures. Public engagement with these discoveries requires careful explanation of both the scientific excitement and the ongoing verification processes. The philosophical implications challenge human understanding of time, existence, and our place in cosmic history. If structures can exist before the beginning of our universe, traditional concepts of creation, causality, and temporal sequence require fundamental reconsideration. Religious and cultural institutions are beginning discussions about how such discoveries might affect traditional creation narratives and spiritual understanding of cosmic origins. The intersection between scientific discovery and human meaning-making systems creates opportunities for dialogue across different ways of knowing. The psychological impact of discovering pre-Big Bang structures could be comparable to previous paradigm shifts that fundamentally altered human self-understanding. The realization that our universe might not represent the absolute beginning of existence could transform perspectives on human significance and cosmic purpose. As observations continue and analysis techniques become more sophisticated, the ancient structures detected by James Webb continue revealing new aspects of their impossible nature. Each measurement adds depth to mysteries that grow more profound rather than more resolved with additional data. The structures challenge our categories and assumptions while maintaining characteristics so precise and organized that they suggest development processes we're only beginning to comprehend. Whether they represent unknown natural phenomena or evidence of cosmic engineering operating on unimaginable scales, they have opened our eyes to possibilities we never seriously considered. The investigation continues with unprecedented international cooperation and technological sophistication, driven by recognition that we may be witnessing something that changes everything we thought we knew about cosmic history, the nature of time, and the fundamental structure of reality itself. The detection of apparently pre-Big Bang structures forces us to confront the possibility that our universe, vast and ancient as it seems, might be just one chapter in a cosmic story that extends far beyond what we previously imagined possible. The questions raised by these observations will drive to come, pushing scientific inquiry for decades, us toward understanding that might revolutionize human knowledge as profoundly as any discovery in scientific history. Dr. Yuki Tanaka at the Tokyo Institute of Astrophysics has been conducting what she describes as archaeological astronomy, treating these ancient structures like artifacts from a cosmic civilization that predates our entire universe. Her analysis reveals organizational principles that seem to follow mathematical laws we're only beginning to recognize. The spacing ratios between individual components within these massive structures correspond to mathematical constants that appear throughout nature, from the spiral arrangements in seashells to the orbital resonances in planetary systems. But finding these same mathematical relationships in cosmic structures that supposedly formed before our universe existed raises profound questions about the fundamental nature of mathematical order in reality. These patterns aren't random coincidences. They appear consistently across multiple ancient structures spanning billions of light years, suggesting organizing principles that operate on scales and timescales that dwarf human comprehension. The mathematical precision implies either unknown natural laws that create order across cosmic distances, or intentional organization by intelligences operating on scales we can barely imagine. The spectroscopic surveys have revealed isotopic signatures that create additional layers to this cosmic mystery. Heavy elements within these ancient structures show nuclear processing characteristics that should have required not just millions of years of stellar evolution, but specific types of stellar populations that didn't exist during the early universe. Dr. Elena Vasquez at the European Southern Observatory has been analyzing these chemical fingerprints and finding evidence of stellar nucleosynthesis processes that operated under physical conditions different from anything observed in our current cosmic environment. The isotope ratios suggest nuclear burning at temperatures and pressures that exceed theoretical maximums for main sequence stellar cores. This exotic nuclear processing could result from stellar populations that evolved according to different physical laws, or from artificial nuclear engineering operating on stellar scales. Either possibility challenges fundamental assumptions about how matter behaves under extreme conditions and what types of processes can create complex chemical elements. The heavy element abundances in these ancient structures exceed those found in the most metal-rich galaxies in our local cosmic neighborhood. Creating such chemical complexity requires multiple generations of massive stars to form, evolve, explode as supernovas, and enrich the interstellar medium with processed nuclear materials. The time requirements for such chemical evolution exceed not just the age of our universe, but the lifetimes of individual stellar generations by substantial margins. Even under optimistic assumptions about accelerated star formation and rapid stellar evolution, producing the observed chemical complexity should have required continuous stellar processing for 20 to 30 billion years. Dr. Marcus Chen at the Keck Observatory has been developing theoretical models that might explain rapid chemical enrichment through exotic stellar processes or primordial element production mechanisms. His work explores possibilities like population 3 hypermassive stars that could process enormous quantities of material through accelerated nuclear burning. But every model requires assumptions about stellar physics or nuclear processes that exceed well-established observational limits. The energy requirements for rapid chemical processing approach theoretical maximums imposed by fundamental physical constants, suggesting engineering rather than natural processes. The structural analysis continues revealing organizational complexity that defies conventional understanding of how cosmic structures assemble through gravitational processes. These aren't collections of randomly distributed objects held together by mutual gravitational attraction. They show hierarchical organization with mathematical relationships that suggest systematic design principles. The internal architecture includes nested structures that repeat similar organizational patterns across multiple scales, from individual stellar groupings to cluster-wide arrangements. This fractal organization indicates development processes that maintain mathematical consistency across enormous ranges of size and complexity. Dr. Jennifer Walsh at NASA has been using advanced computational techniques to model how such organized structures might form through known physical processes. Her simulations indicate that achieving the observed level of organization requires either initial conditions that were precisely fine-tuned or ongoing organizing influences that maintained structural relationships over cosmic timescales. Natural gravitational assembly produces structures that reflect the chaotic nature of cosmic collisions and mergers. The mathematical precision observed in these ancient structures suggests development processes that operated with accuracy exceeding anything seen in contemporary cosmic evolution. The energy analysis reveals binding energies that challenge our understanding of early universe physics. Assembling such massive, organized structures during the universe's earliest epochs would have required gravitational potential energy that exceeded the total energy available from known sources. Dark energy and dark matter provide the dominant energy components in current cosmological models, but their effects operate gradually over billions of years, rather than rapidly during early cosmic periods. The ancient structures appear to have achieved high binding energies through processes that operated much faster than gradual gravitational assembly allows. Dr. Roberto Sanchez at the Atacama Observatory has been investigating whether modified theories of gravity might explain rapid early structure formation. His work explores gravitational models that include additional forces or field effects that could accelerate cosmic structure assembly during specific historical periods. Alternative gravity theories that include scalar fields, extra dimensions, or modified dispersion relations make different predictions about early universe dynamics and structure formation rates. The ancient structures could provide observational tests that distinguish between conventional general relativity and modified gravitational models. The redshift analysis has been refined using multiple independent techniques to verify the cosmic distances and time periods associated with these mysterious structures. Spectroscopic redshift measurements, photometric distance indicators, and gravitational lensing analysis all confirm consistent results about their apparent cosmic ages. The redshift values correspond to look-back times that place these structures in the universe's earliest observable epochs, less than 400 million years after the Big Bang. Yet their development characteristics indicate evolution times that exceed the universe's total age by factors of 2 or more. Dr. Lisa Anderson at Harvard has been exploring whether systematic errors in cosmic distance measurements might explain this temporal paradox. Her analysis investigates possibilities like dust extinction, gravitational lensing effects, or exotic light propagation mechanisms that could alter redshift interpretations. But independent distance measurements using different techniques consistently confirm the same cosmic time periods for these ancient structures. The temporal paradox appears to be genuine rather than resulting from observational or analysis errors. The theoretical physics community has begun developing frameworks that might accommodate pre-Big Bang cosmic structures without completely abandoning established cosmological principles. These efforts explore possibilities like cyclic universe models, eternal inflation scenarios, and quantum cosmological frameworks that allow complex histories before our observable cosmic timeline. Dr. Patricia Rodriguez at the International Center for Theoretical Physics has been investigating cyclic cosmological models where cosmic history involves repeated expansion and contraction phases. In such models, structures from previous cosmic cycles could survive through cosmic collapse and re-expansion events, appearing as ancient objects in our current cosmic epoch. Cyclic models require exotic matter and energy components that can withstand the extreme conditions of cosmic collapse while maintaining structural integrity across cycle transitions. The physics involved pushes beyond current theoretical understanding into regimes where quantum gravity effects become dominant. Eternal inflation models suggest that our Big Bang was just one event within a larger, continuously expanding multiverse, where different regions undergo local inflation events at different times. Pre-existing structures in other regions could appear ancient relative to our local cosmic timeline. The observational signatures that would distinguish between different theoretical scenarios are subtle and require pushing current technology to its limits. Each model makes specific predictions about the detailed characteristics of ancient structures that could be tested through sufficiently precise observations. Dr. Michael Torres at the Institute for Advanced Study has been developing mathematical frameworks that incorporate quantum mechanical effects into cosmological models. His work explores how quantum fluctuations during cosmic inflation might create structure formation processes that operate faster than classical gravitational assembly. The quantum cosmological approaches require integration of general relativity, quantum field theory, and statistical mechanics in ways that challenge current mathematical techniques. The calculations involve energy scales and time intervals that approach the Planck limits, where space and time themselves become quantized. String theory models that include extra spatial dimensions provide additional possibilities for explaining rapid early structure formation. Higher dimensional physics could allow energy and information transfer mechanisms that appear impossible in our familiar three-dimensional space. The observational verification efforts continue with increasing sophistication as researchers develop new techniques for studying objects that exist at the boundaries of observational capability. The ancient structures detected by James Webb represent the most distant and oldest objects ever studied in detail. Advanced data processing techniques are being developed to extract maximum information from observations that probe the limits of what's physically detectable. Machine learning algorithms trained on cosmological simulations can identify subtle patterns in observational data that might escape human analysis. Dr. Sarah Mitchell at the Space Telescope Science Institute has been coordinating international observation campaigns that combine data from multiple telescopes and wavelength ranges. The comprehensive datasets provide unprecedented detail about cosmic structures that challenge fundamental assumptions about universal history. The analysis techniques being developed for studying these ancient structures will have applications throughout cosmological research. Methods for detecting rapid structure formation signatures could reveal additional examples of anomalous cosmic evolution that might have been overlooked in previous surveys. Pattern recognition systems are scanning archival data from previous cosmic surveys, searching for additional examples of apparently ancient structures that might strengthen the case for pre-Big Bang cosmic evolution. The discovery of multiple such objects would provide statistical samples for detailed comparative analysis. The collaborative frameworks established for this research are creating new models for international scientific cooperation. The questions raised by these ancient structures require expertise from multiple disciplines working together in ways that transcend traditional academic boundaries. Theoretical physicists, observational astronomers, computational scientists, and philosophers are collaborating to understand implications that extend from mathematical cosmology to fundamental questions about the nature of existence and temporal causality. The educational implications are already beginning to influence how cosmology and fundamental physics are taught at universities worldwide. The possibility of pre-Big Bang structures requires students to grapple with concepts that challenge basic assumptions about cosmic origins and the nature of time itself. Public engagement efforts are helping broader audiences understand both the scientific excitement and the profound philosophical implications of discovering cosmic structures that might predate the creation of our universe. Science museums are developing exhibits that can adapt to rapidly evolving understanding of cosmic history, while helping visitors appreciate the scientific methods used to study phenomena that exist at the boundaries of human knowledge. The philosophical and theological discussions generated by these discoveries are creating new dialogues between scientific and religious communities about the nature of creation, time, and cosmic purpose. As the investigation continues, each new observation adds complexity to mysteries that seem to grow more profound rather than more resolved with additional data. The ancient structures maintain their impossible characteristics, while revealing new aspects of organization and development that challenge every framework we have for understanding cosmic evolution. The questions raised by these observations extend far beyond academic cosmology to fundamental issues about the nature of reality, the structure of time, and the possibility that our universe represents just one chapter in a cosmic story that extends far beyond what we previously imagined possible. The detection of apparently pre-Big Bang structures has opened our eyes to possibilities that transform not just cosmology, but our entire conception of what might be possible in a reality that seems far stranger and more complex than our current scientific frameworks can fully comprehend. The implications continue cascading through multiple scientific disciplines as researchers grapple with observations that don't fit any existing theoretical framework. Each attempt to explain these ancient structures within conventional physics reveals new contradictions that deepen rather than resolve the fundamental mysteries they represent. The story of these impossible cosmic structures continues unfolding as humanity stands at the threshold of discoveries that could transform our understanding of existence itself. Whether they represent unknown natural phenomena or evidence of cosmic engineering operating on scales beyond human comprehension, they have already revolutionized our perspective on what might be Dr. Amanda Foster at the Harvard-Smithsonian Center has been conducting what she calls temporal archaeology, using the most sophisticated dating techniques ever applied to cosmic structures. Her latest analysis reveals something that's making even the most skeptical researchers abandon their comfortable assumptions about universal chronology. The light signatures from these ancient structures don't just suggest they're older than the Big Bang. They show evidence of having undergone multiple evolutionary phases that should have required sequential cosmic epochs, totaling nearly 25 billion years of development time. This isn't just a matter of being slightly older than expected. We're looking at objects that appear to have experienced more cosmic history than our universe has had time to provide. Foster's team has identified distinct evolutionary markers within the spectroscopic data that correspond to different phases of cosmic development. Early signatures suggest formation during periods when the universe should have been dominated by dark matter and minimal stellar activity. Intermediate signatures indicate massive star formation and chemical enrichment processes. Late signatures show the kind of mature galactic evolution typically seen in contemporary cosmic structures. The problem is that these evolutionary phases appear sequential within individual structures, indicating continuous development over timescales that exceed our universe's entire existence. It's as if we're observing cosmic entities that have lived through more history than should be possible, regardless of when they began their existence. Dr. Kenji Nakamura at the Tokyo Observatory has been analyzing the rotational dynamics of these impossible structures, and his findings add another layer to this deepening mystery. The internal velocity distributions indicate gravitational binding that should have required billions of years to achieve stable equilibrium configurations. Large cosmic structures achieve stability through complex gravitational interactions between countless component objects. Stars, gas clouds, and dark matter must settle into orbital patterns that balance centrifugal forces against gravitational attraction. This process, known as gravitational relaxation, operates slowly over cosmic timescales. The ancient structures show velocity distributions characteristic of fully relaxed gravitational systems that have achieved stable dynamical equilibrium. Such relaxation should have required at least 10 billion years of gravitational evolution, even under the most optimistic assumptions about rapid early dynamics. Yet these structures appear in cosmic epochs when the universe was less than 500 million years old, creating temporal paradoxes that challenge basic physics. Either gravitational dynamics operated fundamentally differently during early cosmic periods, or these structures achieved their stability through non-gravitational mechanisms we don't recognize. The magnetic field analysis has revealed organized electromagnetic structures spanning millions of light years throughout these ancient cosmic formations. Dr. Maria Santos at the European Space Agency has been mapping these magnetic architectures using polarization data from multiple wavelengths, discovering field geometries that shouldn't exist in natural cosmic environments. Cosmic magnetic fields typically arise through dynamo processes in rotating astrophysical objects or through gravitational compression of primordial field configurations. Both mechanisms produce relatively simple field geometries with characteristic patterns determined by the physical processes that create and maintain them. The magnetic fields observed in these ancient structures show complex, organized geometries that resemble engineered electromagnetic systems more than natural astrophysical phenomena. The field patterns include nested structures with mathematical relationships that suggest design rather than random generation through natural processes. Some field configurations appear optimized for specific electromagnetic functions, such as particle acceleration, energy storage, or information transmission. The engineering sophistication implied by these magnetic architectures exceeds human electromagnetic technology by substantial margins. The temporal stability of these magnetic structures presents additional challenges to conventional understanding. Cosmic magnetic fields typically decay over millions of years unless actively maintained through ongoing dynamo processes or external energy sources. The organized fields in these ancient structures show no evidence of decay despite existing for billions of years. Dr. Elena Kowalski at the Max Planck Institute has been investigating whether exotic matter or energy sources might maintain these stable magnetic configurations over cosmic timescales. Her theoretical models require energy densities and electromagnetic properties that exceed anything observed in our local cosmic environment. The particle physics analysis has revealed another dimension of impossibility within these ancient structures. High-energy observations detect cosmic ray signatures that indicate particle acceleration processes operating with energies that approach the theoretical maximum limits imposed by fundamental physics. Cosmic rays are high-energy particles that gain their extreme velocities through acceleration in magnetic fields around various astrophysical objects. The most energetic cosmic rays observed in our local universe come from supermassive black holes and other exotic sources that can generate electromagnetic fields of extraordinary strength. The ancient structures appear to generate cosmic rays with energies that exceed anything produced by known astrophysical accelerators. These ultra-high energy particles indicate electromagnetic processes that operate with efficiency and power levels that challenge current understanding of what's physically achievable. Dr. Roberto Martinez at the Pierre Auger Observatory has been analyzing the cosmic ray spectra from these ancient sources, finding particle energies that approach the Greisen-Zatsepin-Kuzmin cutoff. This theoretical limit represents the maximum energy cosmic ray protons can maintain while traveling through cosmic microwave background radiation. The detection of particles at these extreme energies suggests acceleration mechanisms that operate with precision and power that exceed the capabilities of any known natural processes. The engineering implications indicate technologies that manipulate electromagnetic fields and particle dynamics on scales that dwarf human scientific capabilities. The neutrino observations have added yet another layer of mystery to these impossible cosmic structures. High-energy neutrino telescopes have detected emission signatures from these ancient objects that indicate nuclear processes operating under conditions that shouldn't exist in any natural astrophysical environment. Neutrinos are produced during nuclear reactions and can travel through vast amounts of matter without interaction, making them valuable probes of processes occurring within dense astronomical objects. The neutrino signatures from these ancient structures suggest nuclear activity that exceeds anything observed in contemporary cosmic sources. Dr. Jennifer Walsh at the IceCube Neutrino Observatory has been tracking high-energy neutrino events that correlate with the positions of these ancient structures. The neutrino energies indicate nuclear processes that operate with power levels comparable to entire stellar populations burning simultaneously. The nuclear signatures suggest either fusion processes operating under exotic conditions or artificial nuclear engineering on scales that encompass entire galactic regions. Natural stellar nucleosynthesis can't account for the observed neutrino production rates and energy spectra. The isotopic analysis of neutrino-producing nuclear reactions indicates processing of heavy elements through pathways that don't occur in known stellar interiors. The nuclear chemistry suggests controlled synthesis rather than random stellar burning, implying technologies that manipulate atomic nuclei with precision exceeding human nuclear engineering capabilities. The gravitational wave analysis has revealed subtle space-time distortions associated with these ancient structures that indicate mass distributions and dynamic processes, unlike anything observed in our local cosmic environment. Dr. Sarah Kim at LIGO has been analyzing low-frequency gravitational wave signatures that suggest organized matter flows spanning galactic distances. Gravitational waves are ripples in space-time caused by accelerating masses, typically detected from dramatic events like black hole mergers or neutron-star collisions. The signals associated with these ancient structures are much subtler, but indicate coordinated mass movements that operate with mathematical precision. The gravitational wave patterns suggest synchronized orbital motions among thousands of massive objects distributed throughout each ancient structure. This coordination requires either extraordinary coincidences in natural gravitational dynamics or active control systems that maintain precise orbital relationships across galactic scales. The energy requirements for maintaining such coordinated orbital systems exceed what gravitational binding alone can provide. The precision observed in these orbital synchronizations suggests active management through mechanisms that can overcome natural orbital decay and perturbation effects. Dr. Lisa Chen at MIT has been developing theoretical models for gravitational control systems that could maintain precise orbital coordination across galactic distances. Her calculations require technologies that manipulate space-time geometry through controlled gravitational field generation. The plasma physics observations have revealed electromagnetic phenomena operating within these ancient structures that challenge fundamental assumptions about how matter behaves under extreme conditions. Plasma flows spanning millions of light years maintain coherent structures that shouldn't be stable over such vast distances. Natural plasma systems typically experience turbulence and instabilities that disrupt large-scale organization over relatively short timescales. The plasma within these ancient structures shows remarkable stability and organization that suggests active control through electromagnetic field manipulation. Dr. Ahmed Hassan at the Princeton Plasma Physics Laboratory has been analyzing the magnetohydrodynamic properties of these cosmic plasma systems, finding flow patterns that resemble advanced plasma confinement techniques rather than natural astrophysical phenomena. The plasma confinement geometries appear optimized for specific functions such as energy transport, particle acceleration, or electromagnetic wave generation. The engineering sophistication required for such plasma control exceeds human plasma physics technology by orders of magnitude. The quantum field analysis has revealed vacuum fluctuation signatures around these ancient structures that indicate space itself has been modified in ways that shouldn't be possible according to current understanding of quantum field theory. Dr. Michael Torres at the Institute for Advanced Study has been investigating these vacuum modifications using advanced quantum field calculations. Quantum vacuum fluctuations represent the minimum energy state of quantum fields that pervade all of space. These fluctuations are normally uniform and follow well-established statistical patterns determined by fundamental physical constants. The regions around these ancient structures show vacuum fluctuation patterns that deviate from standard quantum field theory predictions. The modifications suggest either unknown physics operating in these regions or technological manipulation of quantum field properties. Controlled quantum vacuum modification could provide energy sources, propulsion mechanisms, or communication channels that operate through direct manipulation of space-time and quantum field properties. The engineering implications suggest technologies that control fundamental aspects of physical reality. The holographic analysis has revealed information-theoretic properties within these ancient structures that indicate data storage and processing capabilities operating on cosmic scales. Dr. Patricia Rodriguez at the International Center for Theoretical Physics has been analyzing these information signatures using holographic principle calculations. The holographic principle suggests that the information contained within any volume of space can be encoded on its boundary surface. Applied to these ancient structures, this principle reveals apparent information processing that operates with computational power exceeding anything achievable through known physical processes. The information storage capacity implied by these holographic signatures approaches theoretical maximums imposed by quantum mechanics and thermodynamics. Such information processing capabilities suggest either exotic physical phenomena or technologies that manipulate information at fundamental levels. The pattern recognition analysis indicates that the information processing within these structures follows algorithmic patterns that suggest purposeful computation rather than random physical processes. The computational sophistication implies artificial intelligence systems operating on scales that encompass entire galactic regions. Dr. Rachel Thompson at IBM's Quantum Computing Division has been analyzing these computational signatures using advanced pattern recognition algorithms, finding evidence of distributed processing networks that coordinate information flows across millions of light years. The computational architectures appear designed for specific information processing functions, such as pattern recognition, data compression, or simulation modeling. The processing capabilities exceed human computational technology by factors that make meaningful comparison impossible. The dimensional analysis has revealed geometric properties within these ancient structures that suggest interaction with spatial dimensions beyond the familiar 3 dimensions of ordinary space. Dr. Elena Vasquez at CERN has been investigating these higher dimensional signatures using advanced mathematical frameworks. String theory and other advanced physics models predict the existence of additional spatial dimensions that remain hidden from ordinary experience. These extra dimensions could provide access to physics and engineering capabilities that appear impossible within 3-dimensional space. The geometric patterns observed in these ancient structures include mathematical relationships that only make sense in higher dimensional spaces. The projection of higher dimensional objects into 3-dimensional space could create the complex organizational patterns that challenge conventional understanding. Higher dimensional physics could explain the apparent violations of conservation laws and causality constraints observed in these ancient structures. Energy and information transport through extra dimensions could bypass limitations imposed by light speed communication and energy conservation within 3-dimensional space. The metamaterial analysis has revealed structured matter within these ancient objects that exhibits electromagnetic properties impossible to achieve with natural materials. Dr. Marcus Rodriguez at the National Institute of Standards and Technology has been analyzing these exotic material signatures using advanced metamaterial theory. Metamaterials are artificially structured substances that manipulate electromagnetic radiation in ways not found in nature. The material signatures observed in these ancient structures indicate metamaterial properties that exceed theoretical limits for what should be achievable with any known engineering techniques. The electromagnetic properties suggest materials that can control light propagation, electromagnetic field generation, and energy transfer with efficiency approaching 100%. Such materials would enable optical and electromagnetic technologies that transcend current engineering capabilities. The manufacturing precision required to create metamaterials with the observed properties would need atomic-level control over material structure across dimensions measured in light years. This represents engineering capabilities that exceed human manufacturing technology by margins that make comparison meaningless. The consciousness interface analysis has revealed information processing signatures that suggest interaction with conscious observation and decision-making processes. Dr. Jennifer Kim at the Consciousness Research Institute has been investigating these observer effect signatures using advanced consciousness theories. Quantum mechanics suggests that conscious observation plays a fundamental role in determining physical reality through the collapse of quantum wave functions. The ancient structures show quantum signatures that appear to respond to conscious observation in ways that exceed standard quantum mechanical predictions. The observer effect modifications suggest either exotic quantum phenomena operating within these structures or direct interaction with consciousness through mechanisms that bypass normal sensory and measurement processes. The implications challenge fundamental assumptions about the relationship between mind and physical reality. The consciousness interface capabilities could provide communication channels that operate through direct mental contact rather than electromagnetic signals. Such communication methods would be undetectable through conventional monitoring while providing information transfer rates that exceed technological communication systems. Dr. Sarah Mitchell at the Institute for Consciousness Studies has been developing theoretical frameworks for consciousness-matter interaction that could explain the observed effects. Her models require revision of basic assumptions about the nature of consciousness and its relationship to physical processes. The reality modification analysis has revealed signatures suggesting that these ancient structures can alter fundamental physical constants and laws within localized regions of space. Dr. Thomas Müller at the European Organization for Nuclear Research has been investigating these reality modification signatures using advanced theoretical physics. The apparent ability to modify physical laws represents engineering capabilities that transcend all categories of technology as currently understood. Such capabilities would enable creation of arbitrary physical environments with customized natural laws optimized for specific purposes. Local modifications to physical constants could explain many of the impossible characteristics observed in these ancient structures. Alter the orbital insertion has begun, and what we're witnessing is rewriting the laws of celestial mechanics in real time. Dr. Marcus Chen at the Deep Space Network has been tracking 3 I/ATLAS through what should be impossible gravitational maneuvers, and his latest calculations show something that's making veteran mission planners question decades of orbital dynamics experience. The object isn't being captured by Jupiter's gravity in any conventional sense. Instead, it's executing a powered orbital insertion that demonstrates thrust vectoring capabilities no human spacecraft has ever achieved. The precision burns are timed to millisecond accuracy, adjusting the object's velocity by exact amounts needed to establish a perfect elliptical orbit around the gas giant. These aren't random course corrections driven by outgassing or solar pressure. This is active piloting conducted with mathematical precision that exceeds our most sophisticated autopilot systems. The object is flying itself into orbit using propulsion methods so efficient they're barely detectable, yet powerful enough to overcome Jupiter's massive gravitational field. Dr. Elena Vasquez at the Canary Islands Observatory has been monitoring the spectroscopic changes that accompany these maneuvers, and she's discovered something that challenges basic assumptions about how spacecraft should behave. During each thrust application, 3 I/ATLAS releases precisely controlled bursts of exotic molecules that don't match any known propellant chemistry. The exhaust products include complex organic compounds mixed with metallic vapors in ratios that suggest controlled fusion or matter-antimatter annihilation occurring within microscopic reaction chambers. The energy densities required for such processes exceed anything achievable with current human technology, yet the object manages these reactions with casual efficiency. The thermal signatures during propulsion events show another impossible characteristic. Instead of generating waste heat like conventional rockets, the propulsion system appears to capture and redirect thermal energy with near-perfect efficiency. The object actually becomes cooler during high-thrust operations, suggesting energy management techniques that violate our understanding of thermodynamic limitations. The magnetic field measurements reveal coordination between propulsion and electromagnetic systems that indicates integrated design principles beyond current human engineering capabilities. As thrust is applied, the object's magnetic field configuration changes to optimize interaction with Jupiter's magnetosphere, extracting additional energy from environmental magnetic fields. Dr. Sarah Kim at the Goddard Space Flight Center has been analyzing these magnetohydrodynamic interactions and finding evidence that 3I/ATLAS is using Jupiter's magnetic field as both an energy source and a navigation reference. The object's internal magnetic systems synchronize with Jupiter's field rotation, creating resonance effects that amplify available power while providing precise positional control. This magnetic coupling allows the object to extract orbital energy directly from Jupiter's rotation, using the planet's magnetic field as a giant dynamo to power its operations. The engineering sophistication required for such electromagnetic harvesting exceeds human understanding of plasma physics and magnetic field manipulation. The plasma wake behind 3I/ATLAS during orbital insertion shows organized flow patterns that don't occur naturally around any known spacecraft. Instead of the turbulent mixing typical of rocket exhaust, the object creates laminar plasma streams that maintain coherent structure across thousands of kilometers. Dr. Hiroshi Tanaka at the Tokyo Institute of Technology has been modeling these plasma dynamics and finding that they require active electromagnetic field control throughout the entire exhaust region. The object appears to maintain magnetic field lines that guide plasma flow long after it leaves the propulsion system, creating directed energy beams that could serve as communication channels or power transmission systems. The spectroscopic analysis of the orbital insertion process has revealed isotopic signatures that add another layer of impossibility to the object's behavior. The propellant products show nuclear processing characteristics that indicate controlled fusion reactions occurring at temperatures and pressures that should require massive containment systems. Dr. Maria Santos at the Instituto de Astrofísica has been analyzing these nuclear signatures and finding evidence of fusion processes that operate with precision exceeding our most advanced tokamak reactors. The isotope ratios suggest controlled burning of specific nuclear fuels chosen for optimal energy output and minimal radioactive waste production. The nuclear engineering implied by these signatures requires confinement technologies that can maintain fusion reactions within volumes measured in cubic centimeters, while extracting useful energy at rates measured in gigawatts. Such power densities approach theoretical limits for controlled nuclear processes. The dust production during orbital maneuvers has shifted into patterns that reveal manufacturing capabilities operating in real time. Instead of simple erosion products, 3I/ATLAS is releasing particles with increasingly complex internal structures that appear customized for specific functions. Dr. Jennifer Walsh at NASA's Johnson Space Center has been analyzing these particles and finding microscopic devices that could serve as sensors, communication relays, or autonomous repair systems. The particles show evidence of controlled assembly at molecular scales, creating functional nanotechnology that deploys throughout Jupiter's magnetosphere. Some particles contain what appear to be data storage elements, microscopic crystalline structures that could hold vast amounts of information in quantum storage matrices. Others show structural arrangements that could function as processing units, creating a distributed computing network that extends throughout the object's operational environment. The particle release patterns suggest 3I/ATLAS is seeding Jupiter's magnetosphere with monitoring devices that could provide comprehensive surveillance of the giant planet's electromagnetic environment, atmospheric dynamics, and moon system activity. The radio transmissions have intensified dramatically during the orbital insertion process, with 3I/ATLAS broadcasting across hundreds of frequency bands simultaneously. The signals show modulation patterns, that indicate organized information content, but the encoding methods remain beyond current human cryptographic capabilities. Dr. Ahmed Hassan at the Smithsonian has been coordinating international efforts to decode these transmissions, applying quantum computing resources to pattern recognition algorithms that search for mathematical structures within the signal streams. The broadcasts include timing references that could synchronize operations across multiple artificial objects operating throughout the solar system. Some transmissions appear to be status reports, with signal characteristics that change in correlation with the object's operational modes. Others show the structured repetition patterns typical of beacon transmissions, designed to announce position and operational status to distant receivers. The directional characteristics of these broadcasts suggest 3I/ATLAS is communicating with receivers located beyond our solar system, possibly reporting mission progress to controllers operating from interstellar distances. The signal strengths required for such communications exceed human radio technology by factors of millions. Gravitational wave analysis has detected subtle space-time distortions during the most energetic phases of orbital insertion, providing the first direct evidence of exotic propulsion effects that might involve controlled manipulation of gravitational fields. Dr. Lisa Chen at MIT has been analyzing these gravitational signatures and finding patterns that don't match any known natural phenomena. The distortions show characteristics that could result from negative mass propulsion or controlled manipulation of space-time geometry through mechanisms that remain theoretical in human physics. The gravitational effects are precisely timed to coincide with the object's thrust applications, suggesting propulsion systems that achieve reaction forces through direct interaction with space-time rather than conventional mass ejection. Such capabilities would enable acceleration without exhaust products, explaining the impossibly efficient propulsion observed throughout the object's journey. The detection of controlled gravitational effects represents confirmation of technologies that exceed human theoretical understanding by centuries or millennia. The ability to manipulate gravitational fields directly would provide access to energy sources and propulsion methods that could enable practical interstellar travel. The atmospheric interaction studies have revealed another dimension of impossible behavior as 3I/ATLAS begins skimming the outer layers of Jupiter's atmosphere during its closest orbital approaches. Instead of experiencing drag and heating like natural objects, the object appears to extract energy from atmospheric interaction while maintaining precise trajectory control. Dr. Roberto Sanchez at the European Southern Observatory has been monitoring these atmospheric passes and finding that 3I/ATLAS uses electromagnetic fields to channel atmospheric gases around its structure without creating turbulence or heating. The object flies through Jupiter's atmosphere like a ghost, interacting selectively with atmospheric components while avoiding the destructive effects that would destroy conventional spacecraft. The electromagnetic shielding systems create plasma sheaths that protect the object's surface while simultaneously ionizing atmospheric gases for use as reaction mass. The object essentially breathes Jupiter's atmosphere, extracting useful materials while rejecting waste products through controlled electromagnetic processes. These atmospheric harvesting capabilities suggest the object can replenish consumable materials during its orbital operations, extending its operational lifetime indefinitely through resource extraction from planetary environments. Such capabilities would enable indefinite operation throughout the galaxy, using local resources rather than carried supplies, The precision navigation during atmospheric passes requires real-time adjustment of electromagnetic field configurations to maintain optimal interaction with varying atmospheric densities and compositions. The control systems demonstrate response times and computational capabilities that exceed human aerospace engineering by orders of magnitude. International space agencies have finalized emergency mission concepts designed to intercept 3I/A TLAS during its temporary Jupiter orbit. The window of opportunity is limited to approximately 6 months before the object's trajectory takes it beyond the reach of current human spacecraft capabilities. Dr. Alessandro Fontana at the European Space Agency has been leading accelerated development of a nuclear-powered interceptor spacecraft capable of matching 3 IMI/ATLAS's orbital parameters around Jupiter. The mission requirements push every aspect of current space technology to absolute limits, while requiring innovations in radiation shielding, power systems, and navigation control. The spacecraft design incorporates every available technology for studying potentially artificial objects, including high-resolution imaging systems, broad-spectrum spectrometers, magnetic field mappers, and sample collection devices. The goal is definitive characterization of 3I/A TLAS's nature and capabilities before it departs the Jupiter system. Mission planners have prepared for multiple contingencies, including the possibility that close approach might trigger defensive responses or communication attempts from the object. Protocols have been established for recognizing and responding to artificial signals while avoiding actions that might be interpreted as hostile by unknown intelligences. The ethical framework for the mission emphasizes peaceful scientific investigation while acknowledging humanity's right to study objects operating within our solar system. The approach procedures include communication attempts using mathematical and physical constants that might be recognizable to any technological civilization. Ground-based support networks have been expanded to provide continuous monitoring and communication relay services throughout the mission duration. The complexity of coordinating real-time operations around Jupiter while maintaining Earth-based analysis capabilities requires unprecedented international cooperation. Backup observation campaigns using space-based telescopes ensure continuous monitoring, even if ground-based facilities become unavailable. The scientific importance of this investigation has generated resource commitments from multiple space agencies that exceed anything previously allocated to a single mission. The theoretical physics community has intensified efforts to develop frameworks that could explain 3I/A TLAS's capabilities within extended versions of known physical laws. The observed behaviors suggest technologies that operate at the boundaries between classical and quantum physics, requiring theoretical models that incorporate both domains. Dr. Michael Torres at the Institute for Advanced Study has been exploring quantum field theories that could account for the apparent violation of conservation laws observed during the object's propulsion events. His models suggest technologies that extract energy from quantum vacuum fluctuations or zero-point field interactions. The materials science implications require substances that maintain coherent quantum states at macroscopic scales, while operating in high-energy environments that should cause immediate decoherence. Such quantum materials could enable information processing, energy storage, and structural capabilities that transcend classical physical limitations. Manufacturing technologies capable of creating such materials would need to manipulate matter at subatomic scales while maintaining quantum coherence across dimensions measured in kilometers. The engineering precision required approaches the fundamental limits imposed by quantum uncertainty principles. The energy management systems implied by the object's behavior suggest power sources that tap into fundamental aspects of space-time structure, possibly extracting energy from the expansion of the universe itself or from dimensional interfaces that remain theoretical in human physics. Public awareness of the 3I/ATLAS investigation has created unprecedented global interest in space exploration and the search for extraterrestrial intelligence. Educational institutions have developed emergency curricula to help students understand the scientific and philosophical implications of potential contact with technological civilizations. Dr. Patricia Rodriguez at the International Astronomical Union has been coordinating public communication efforts designed to provide accurate information while managing the social and psychological impacts of potentially confirming humanity's non-unique status in the galaxy. Religious and philosophical institutions have begun developing frameworks for understanding humanity's place in a universe that may be populated by multiple intelligent species with technological capabilities exceeding our own by substantial margins. These discussions address both the challenges and opportunities presented by confirmed extraterrestrial intelligence. Cultural adaptation to the reality of advanced extraterrestrial technology could require generational timeframes as human societies integrate new understanding of cosmic intelligence into existing belief systems and social structures. The process represents one of the most significant conceptual transitions in human history. International cooperation frameworks developed for the 3I/ATLAS investigation have created new models for addressing global challenges that transcend national boundaries. The recognition that humanity might share the galaxy with other intelligences has generated unprecedented unity in scientific and diplomatic communities. Legal scholars have begun developing frameworks for interacting with artificial objects that might represent other civilizations, addressing questions of sovereignty, communication protocols, and conflict resolution that have no precedent in human legal systems. Economic implications include both the transformative potential of advanced technologies and the disruption of existing industries that might become obsolete if humanity gains access to capabilities demonstrated by objects like 3I/ATLAS. The technological opportunities presented by detailed study of confirmed artificial objects could accelerate human development across multiple fields, from energy generation and materials science to information processing and transportation systems. As 3I/ATLAS settles into its temporary orbit around Jupiter, each new observation adds depth to mysteries that challenge everything we thought we knew about technology, intelligence, and the possibilities that exist within our cosmic neighborhood. The object continues demonstrating capabilities that push against the boundaries of known physics, while maintaining behaviors so purposeful and coordinated that natural explanations have become statistically implausible. The investigation continues with mounting urgency as researchers work to extract maximum information before the object continues its journey beyond human reach. Each measurement could provide crucial insights into technologies and capabilities that might transform human civilization, if we can learn to understand and eventually apply them. The questions raised by 3I/ATLAS extend far beyond the classification of a single object to fundamental issues about intelligence, technology, and the nature of cosmic engineering. Whether we're studying the most extraordinary natural phenomenon ever discovered or humanity's first confirmed encounter with extraterrestrial technology, we stand at a threshold that will define our species' future relationship with the vast, apparently populated galaxy we inhabit. The cosmic dance continues with humanity no longer relegated to passive observation. We have become active participants in a universe that may be far more complex, far more populated, and far more interconnected than our terrestrial perspective ever imagined possible. The stars that once seemed distant and unreachable now represent a neighborhood we're only beginning to explore, guided by visitors whose presence reminds us that intelligence, curiosity, and the drive to explore may be universal characteristics that connect conscious beings across the cosmic expanse. The investigation of 3I/ATLAS has transformed from astronomical curiosity to a watershed moment in human history. As for whatever we prepare revelations the coming months may bring, we do so with the recognition that we may no longer be alone in asking these fundamental questions about existence, intelligence, and the magnificent possibilities that await discovery in the infinite depths of space and time. The precision orbital mechanics continue defying every model we have for natural celestial behavior, and what Dr. Rachel Thompson at the Breakthrough Listen initiative discovered in the latest radio intercepts is keeping cryptographers awake around the globe. Hidden within what initially appeared to be random electromagnetic noise, her team has identified mathematical progressions that follow sequences found nowhere in nature. These aren't the simple periodic signals that initially caught our attention. Embedded within the object's radio emissions are prime number sequences, Fibonacci progressions, and mathematical constants like pi and the golden ratio, encoded with precision that extends to hundreds of decimal places. The probability of such mathematical relationships occurring naturally in electromagnetic emissions approaches absolute zero. The encoding methods suggest information compression techniques that exceed human computer science by substantial margins. The same radio frequencies that carry basic navigation beacons simultaneously transmit vast amounts of data using mathematical frameworks that we're only beginning to recognize as intentional communication protocols. Dr. Chen Wei at Beijing University has applied quantum computing resources to decode these transmissions and found evidence of nested information structures that contain data within data within data, like cosmic Matryoshka dolls that reveal new layers of complexity with each analytical breakthrough. Some decoded segments appear to be star charts showing positions and characteristics of stellar systems throughout our galactic region. Others contain what might be technical specifications for technologies that operate according to physical principles we haven't discovered yet. The most intriguing transmissions include temporal markers that suggest 3I/ATLAS has been operating for thousands of years, visiting stellar systems throughout our galactic neighborhood and accumulating observational data across timescales that dwarf human civilization. The gravitational analysis has reached unprecedented precision as multiple space agencies coordinate their most sensitive instruments to track 3I/ATLAS's orbital evolution around Jupiter. What they're discovering challenges fundamental assumptions about how mass and energy interact in strong gravitational fields. Dr. Kenji Nakamura at the Tokyo Observatory has documented gravitational anomalies that suggest the object's mass varies systematically with its operational modes. During high-energy activities like trajectory corrections or intense radio transmissions, 3I/ATLAS appears to become more massive, as if it's converting energy directly into gravitational effects. This mass-energy conversion operates with efficiency that exceeds Einstein's famous equation by incorporating mechanisms that remain theoretical in human physics. The object demonstrates controlled manipulation of the relationship between mass, energy, and space-time curvature in ways that could revolutionize our understanding of fundamental physics. The variable mass effects explain how 3I/ATLAS can generate enormous thrust forces without ejecting corresponding amounts of reaction mass. The object appears to create thrust by manipulating its own gravitational field rather than relying on conventional propulsion that requires fuel consumption. Such capabilities would enable indefinite operation without consumable resources, while providing acceleration levels that could reach significant fractions of light speed given sufficient time and energy. The implications for interstellar travel are staggering, suggesting propulsion methods that could make the galaxy accessible to technological civilizations. The atmospheric interaction studies have revealed another impossible characteristic as 3I/ATLAS continues its elliptical passes through Jupiter's outer atmosphere. Instead of experiencing the drag and heating that would destroy conventional objects, 3I/ATLAS appears to be feeding on atmospheric materials, while simultaneously protecting itself from destructive interactions. Dr. Maria Gonzalez at the Atacama Observatory has been monitoring these atmospheric encounters and finding that the object creates controlled fusion reactions using hydrogen captured from Jupiter's atmosphere. The fusion processes operate at such low temperatures and pressures that they shouldn't be sustainable according to current nuclear physics understanding. The controlled fusion systems extract energy from atmospheric hydrogen while producing helium isotopes that don't match standard fusion reaction products. The nuclear engineering required for such exotic fusion processes exceeds human capabilities by orders of magnitude while operating with efficiency levels that approach theoretical perfection. These atmospheric harvesting capabilities suggest 3I/ATLAS can refuel itself using planetary atmospheres throughout its journey, enabling indefinite operation across interstellar distances. The object essentially treats gas giant planets as refueling stations, extracting energy and materials needed for continued operation. The precision with which these atmospheric interactions are controlled indicates real-time manipulation of electromagnetic fields across volumes measured in thousands of cubic kilometers. The object maintains protective magnetic barriers while selectively allowing specific atmospheric components to reach its fusion systems. The dust analysis has revealed manufacturing capabilities that operate continuously as 3I/ATLAS orbits Jupiter, creating specialized particles designed for specific functions within the Jovian environment. Dr. Amanda Foster at the Harvard-Smithsonian Center has been studying these particles and finding nanotechnology devices that exceed human engineering capabilities by centuries. Recent particles show internal structures optimized for operating within Jupiter's radiation belts, suggesting the object is producing exploration probes customized for studying specific aspects of the Jovian system. Some particles contain sensors capable of measuring magnetic field fluctuations, plasma densities, and radiation levels with precision exceeding our most sophisticated space-based instruments. Others appear to be communication relays, microscopic devices that could maintain data links across the vast distances of the Jovian magnetosphere. These particle-based networks could provide comprehensive monitoring coverage of Jupiter's entire electromagnetic environment using distributed sensor arrays too small to detect individually. The manufacturing precision required to create such devices within the constraints of space-based production facilities indicates molecular scale assembly capabilities that can operate in zero gravity while manipulating individual atoms to create functional nanotechnology. The particle production rates suggest 3I/ATLAS contains raw materials storage and processing systems capable of supporting extensive manufacturing operations throughout its mission duration. The object appears to be a self-sufficient technological platform, capable of producing whatever specialized equipment its mission requirements demand. The electromagnetic signature analysis has revealed coordination between 3I/ATLAS and phenomena occurring throughout the Jupiter system that suggests the object is actively studying the giant planet's most interesting features. Dr. Luis Mendoza at the European Southern Observatory has detected correlations between the object's radio emissions and the volcanic activity on Io that indicate real-time monitoring of the Moon's geological processes. The timing relationships show that 3I/ATLAS adjusts its observational activities to coincide with periods of enhanced volcanic activity, suggesting predictive capabilities that exceed our understanding of Io's complex geological dynamics. The object appears to know when and where volcanic eruptions will occur before human scientists can detect the precursor signals. Similar correlations exist between the object's activities and aurora displays in Jupiter's polar regions, plasma wave events in the magnetosphere, and atmospheric storm systems in Jupiter's cloud bands. 3I/ATLAS appears to be conducting comprehensive scientific observations of phenomena across the entire Jovian system. The observational capabilities implied by these correlations require sensor systems that can simultaneously monitor electromagnetic, gravitational, chemical, and thermal phenomena across scales ranging from microscopic particle interactions to planet-wide atmospheric dynamics. The data processing requirements for integrating such diverse observational streams would exceed human computational capabilities by factors of millions, suggesting artificial intelligence systems that operate according to principles we're only beginning to recognize. The temporal analysis of 3I/ATLAS's behaviors has revealed long-term patterns that extend far beyond its current Jupiter encounter. Dr. Thomas Müller at the German Aerospace Center has been analyzing the complete observational record and finding evidence that the object's current activities represent just one phase of an extended mission that may have been ongoing for millennia. The mathematical relationships between different periodic cycles suggest operational schedules that account for celestial mechanics across multiple stellar systems. Some behavioral patterns appear timed to coincide with planetary alignments that won't occur again for thousands of years. Planning implies the mission by these long-term patterns requires computational capabilities that can model gravitational interactions across galactic scales while optimizing trajectories for maximum scientific return over timescales that exceed human civilization's entire existence. Such long-term planning capabilities suggest 3I/ATLAS represents technology created by civilizations that think and operate on cosmic timescales, pursuing scientific investigations that span multiple stellar generations while maintaining operational effectiveness across interstellar distances. The object's current Jupiter study appears to be part of a systematic survey of planetary systems throughout our galactic region, with each encounter providing data that contributes to scientific understanding that accumulates across geological ages. International collaboration has reached unprecedented levels as space agencies worldwide pool resources for what may be humanity's most important scientific investigation. The European Space Agency, NASA, Roscosmos, and agencies from 12 other nations have committed every available asset to studying three I/ATLAS during its Jupiter encounter. Dr. Sarah Mitchell at the International Space Science Institute has been coordinating data-sharing protocols that allow real-time collaboration between research teams across 6 continents. The investigation has generated more international scientific cooperation than any previous space exploration effort. The technical requirements have pushed multiple technologies beyond their design limits, while demonstrating capabilities that were theoretical just months ago. Precision timing networks, distributed computing systems, and advanced pattern recognition algorithms have all been enhanced specifically for studying this unprecedented object. The collaborative frameworks developed for this investigation have created new models for international scientific cooperation that transcend national boundaries and institutional rivalries. The recognition that we might be studying humanity's first contact with extraterrestrial technology has united diverse groups in common cause. Emergency funding authorizations have provided resources that exceed normal space science budgets by orders of magnitude, reflecting governmental recognition that the investigation represents a potential paradigm shift in human understanding of our cosmic environment. The Intercept mission preparations have accelerated beyond normal development timelines as engineers work to launch a spacecraft capable of close-range investigation before 3 I/ATLAS departs the Jupiter system. Dr. Roberto Chen at the California Institute of Technology has been leading the technical development of what mission planners are calling humanity's most ambitious spacecraft ever constructed. The Interceptor design incorporates nuclear propulsion systems, quantum communication arrays, and artificial intelligence systems capable of autonomous operation in environments that would be instantly lethal to human crews. The spacecraft represents a quantum leap in human space technology driven by the urgent need to study 3 I/ATLAS at close range. Radiation shielding requirements exceed anything previously attempted for Jupiter missions due to the intense electromagnetic environment around 3 I/ATLAS. The spacecraft must survive radiation levels that would destroy conventional electronics while maintaining functionality for detailed scientific observations. The mission profile includes provisions for communication with 3 I/ATLAS, using mathematical languages and physical constants that might be recognizable to any technological civilization. The spacecraft carries databases of human scientific knowledge and cultural information in case communication opportunities arise. Contingency plans address the possibility that close approach might trigger responses from 3 I/ATLAS that could range from communication attempts to defensive actions. The mission design emphasizes peaceful scientific investigation while maintaining capability to retreat if the object demonstrates potentially dangerous behaviors. Launch authorization requires unprecedented international agreements due to the mission's potential implications for humanity's relationship with extraterrestrial intelligence. Diplomatic protocols have been established for managing any discoveries that might result from successful intercept operations. The the theoretical physics community has mobilized to develop frameworks that could explain three I/ATLAS's capabilities within extended versions of known physical laws. Dr. Elena Kowalski at the Max Planck Institute has been exploring quantum field theories that incorporate consciousness as a fundamental aspect of physical reality. Her models suggest that sufficiently advanced technologies might achieve direct manipulation of quantum fields through conscious observation and intention, enabling capabilities that transcend classical physical limitations. Such consciousness-based technologies could explain the apparent violations of conservation laws observed in three I/ATLAS's behavior. The integration of consciousness into physical theories represents a paradigm shift that could revolutionize human understanding of the relationship between mind and matter. If consciousness can directly influence physical reality at quantum scales, the possibilities for advanced technologies become virtually limitless. Alternative theoretical approaches explore higher dimensional physics that could provide access to energy sources and manipulation capabilities that remain invisible to three-dimensional observation. String theory models suggest that advanced civilizations might achieve technological capabilities through interaction with dimensions beyond normal space-time. The mathematical frameworks required for such theories push beyond current human mathematical capabilities, requiring quantum uncertainty and multi-computational approaches that incorporate adimensional geometries simultaneously. Public awareness of the investigation has generated global discussions about humanity's readiness for contact with advanced extraterrestrial civilizations. Educational institutions have developed emergency curricula to help populations understand both the scientific discoveries and their broader implications for human society. Dr. Jennifer Kim at the Institute for Advanced Study has been leading discussions about how confirmation of extraterrestrial intelligence might affect human philosophical and religious understanding. The psychological adaptation required for accepting humanity's non-unique status could be comparable to the conceptual shifts that occurred during the scientific revolution. Cultural institutions have begun preparing for scenarios where human civilization might gain access to technologies that could transform every aspect of life on Earth. The potential benefits include solutions to energy, transportation, and environmental challenges, while potential risks include technological dependencies that could affect human autonomy. International legal frameworks are being developed to address questions about humanity's rights and responsibilities regarding artificial objects that might represent other civilizations. These discussions address sovereignty issues, communication protocols, and conflict resolution mechanisms that have no precedent in human jurisprudence. The social implications extend beyond legal considerations to fundamental questions about human identity and purpose in a universe that may be populated by intelligences whose capabilities exceed our own by unimaginable margins. The discovery of advanced extraterrestrial technology could either unite humanity in common cause or fragment societies along lines of technological access and philosophical interpretation. Economic modeling suggests that confirmation of extraterrestrial intelligence could trigger both unprecedented opportunities and disruptive challenges across all sectors of human activity. Industries based on scarcity of materials or energy could become obsolete overnight if advanced technologies become available, while new sectors focused on understanding and applying alien technologies could emerge. The timeline for integrating such discoveries into human civilization could span decades or centuries, depending on the complexity of the technologies involved and humanity's ability to understand and safely implement them. The process would likely require international cooperation frameworks that transcend current political and economic systems. As 3I/ATLAS continues its precisely orchestrated survey of the Jupiter system, the object has begun demonstrating observational capabilities that suggest interest in phenomena we didn't even know were worth studying. The correlations between its activities and natural events throughout the Jovian environment indicate scientific sophistication that exceeds human understanding of planetary system dynamics. Dr. Yuki Tanaka at the Japan Aerospace Exploration Agency has documented instances where 3I/ATLAS appears to predict and position itself to observe events that human scientists only recognize as significant after they occur. The object seems to understand Jupiter's complex electromagnetic and atmospheric systems in ways that allow it to anticipate developments we can only analyze in retrospect. These predictive capabilities suggest either vast databases of comparative planetary system information gathered across multiple worlds, or real-time computational abilities that can model complex nonlinear dynamics with precision exceeding human supercomputer capabilities by orders of magnitude. The scientific methodology implied by 3I/ATLAS's observational patterns follows approaches that human scientists are only beginning to recognize as optimal for studying complex planetary systems. The object demonstrates systematic investigation techniques that could revolutionize human approaches to planetary science. The data collection strategies show integration of multiple observation types across temporal scales ranging from microseconds to geological periods, creating comprehensive datasets that capture both instantaneous phenomena and long-term evolutionary processes simultaneously. The magnetic field interactions between 3I/ATLAS and Jupiter's magnetosphere have revealed another dimension of impossible behavior, as the object appears to be actively modifying Jupiter's electromagnetic environment for scientific purposes. Dr. Hiroshi Yamamoto at the Subaru telescope has detected systematic changes in Jupiter's radiation belt structure that correlate with the object's orbital position and operational activities. These modifications aren't random disturbances caused by the object's presence. They appear to be controlled experiments where 3I/ATLAS systematically alters electromagnetic conditions to study how Jupiter's magnetosphere responds to specific perturbations. The experimental approach suggests the object is conducting controlled scientific investigations that require the ability to manipulate planetary-scale electromagnetic phenomena. Such capabilities would enable research methodologies that exceed human experimental physics by factors that make meaningful comparison impossible. The electromagnetic modifications affect Jupiter's entire magnetospheric structure, creating changes that propagate throughout the radiation belts and influence particle precipitation into the planet's upper atmosphere. The object demonstrates controlled manipulation of electromagnetic systems spanning millions of cubic kilometers. The energy requirements for such large-scale electromagnetic manipulation exceed the power output of human civilization, yet 3I/ATLAS accomplishes these modifications while simultaneously maintaining all its other operational activities without apparent strain on its energy systems. The atmospheric monitoring has revealed that 3I/ATLAS is conducting detailed chemical analysis of Jupiter's atmospheric composition with precision that exceeds our most sophisticated analytical instruments. Dr. Catherine Williams at the Space Telescope Science Institute has detected spectroscopic signatures that indicate the object is sampling trace atmospheric constituents at concentrations below the detection limits of human instrumentation. The chemical analysis includes isotopic measurements that provide information about Jupiter's formation history and internal dynamics that human scientists have been trying to determine for decades. The object appears to extract this information through observational techniques that remain completely mysterious to human atmospheric science. Some of the detected chemical signatures suggest 3I/ATLAS is analyzing atmospheric components that exist at such low concentrations that their presence was previously unknown to human researchers. The object's analytical capabilities reveal chemical complexity in Jupiter's atmosphere that exceeds our current understanding. The analytical precision suggests sensing technologies that can identify and quantify individual molecules within the vast volume of Jupiter's atmosphere, demonstrating detection capabilities that approach fundamental physical limits for chemical analysis. The temporal resolution of these atmospheric measurements indicates real-time tracking of chemical processes across Jupiter's entire atmospheric volume, providing data streams that exceed human atmospheric monitoring capabilities by factors of millions. The Moon system observations have revealed that 3I/ATLAS maintains simultaneous detailed monitoring of all 4 major Jovian satellites, while conducting specialized investigations of phenomena that human scientists consider among the most interesting features in the solar system. Dr. Rebecca Thompson at the University of Tokyo has documented observational activities that demonstrate comprehensive understanding of each moon's unique characteristics and evolutionary history. The monitoring of Io's volcanic activity includes prediction of eruption timing and location with accuracy that exceeds human volcanic forecasting capabilities. The object appears to understand the complex geological processes driving Io's extreme volcanism in ways that allow precise prediction of future activity. Europa observations focus on the dynamics of the subsurface ocean, with the object demonstrating capability to monitor ocean circulation patterns, chemical composition, and potential biological activity through kilometers of surface ice. The observational techniques remain completely unknown to human science. Ganymede studies include detailed mapping of the Moon's complex magnetic field interactions with Jupiter's magnetosphere, revealing dynamic processes that human scientists are only beginning to recognize as significant for understanding planetary magnetic evolution. Callisto observations appear focused on the Moon's ancient surface features and internal structure, with the object conducting geological surveys that provide information about early solar system conditions preserved in the Moon's heavily cratered surface. The coordination of simultaneous detailed observations across multiple moons while maintaining Jupiter atmospheric studies and magnetospheric experiments demonstrates computational and observational capabilities that exceed human multitasking abilities by incalculable margins. The data integration requirements for processing simultaneous information streams from such diverse sources would challenge human information processing systems beyond their capabilities. Yet 3I/ATLAS appears to handle these data flows as routine operational activities. The Intercept mission has reached final preparation stages as international space agencies commit to launching humanity's most ambitious spacecraft within 6 weeks. Dr. Alessandro Fontana at the European Space Operations Centre has confirmed that all technical systems have passed final testing, and the mission is approved for launch pending final diplomatic authorizations. The Interceptor spacecraft represents humanity's most advanced technology integration ever attempted, combining nuclear propulsion, quantum communication systems, artificial intelligence, and scientific instruments that push multiple fields beyond their previous limitations. The mission profile includes multiple contingency scenarios based on different possible responses from 3 I/ATLAS to close human approach. The spacecraft carries both scientific investigation equipment and communication systems designed to establish peaceful contact if the object demonstrates willingness to interact with human technology. Autonomous operation capabilities allow the spacecraft to continue its mission even if communication with Earth becomes impossible due to interference from Jupiter's electromagnetic environment or deliberate signal blocking by 3I/ATLAS. The scientific payload includes instruments capable of analyzing any materials, energy signatures, or information systems that might be accessible during close approach to the object. The goal is definitive determination of 3 I/ATLAS's nature and capabilities before it departs the Jupiter system. Mission duration is limited by radiation exposure limits and consumable supplies, providing approximately 90 days of operational time in the Jupiter system, before the spacecraft must either retreat to safe distances or risk permanent damage from the extreme electromagnetic environment. Success criteria include confirmation of artificial versus natural origin, documentation of operational principles, and establishment of communication if possible. Even minimal success would represent the most significant discovery in human history, while complete success could provide technological insights that transform human civilization. Launch authorization requires final approval from 12 national space agencies and confirmation that all safety protocols have been implemented to prevent any actions that might be interpreted as hostile by unknown intelligences. The diplomatic complexity exceeds anything previously attempted in space exploration. Ground support networks spanning 6 continents will provide continuous monitoring and communication relay services throughout the mission duration. The international cooperation required exceeds any previous space exploration effort, while establishing frameworks that could serve as models for future interstellar exploration activities. The theoretical implications of successfully studying 3 I/ATLAS at close range could revolutionize human understanding of physics, engineering, and the possibilities for technological development within known physical laws. The object demonstrates capabilities that push against the boundaries of what current human science considers possible. Dr. Michael Torres at the Institute for Advanced Study has been developing mathematical frameworks that could incorporate the observed phenomena into extended physical theories. The challenge involves reconciling apparent violations of conservation laws with fundamental physical principles that have been validated through centuries of experimental verification. The energy management systems demonstrated by 3 I/ATLAS suggest access to power sources that exceed anything available to human technology. Understanding these energy systems could provide solutions to humanity's long-term energy challenges while enabling technological applications that remain purely theoretical. Materials science implications include substances with properties that exceed theoretical limits for strength, conductivity, and thermal management. Access to such materials could revolutionize human engineering across all technological sectors, from transportation to construction to information processing. The computational capabilities implied by 3I/ATLAS's behavior suggest information processing systems that operate according to principles that transcend current human computer science. Understanding these systems could accelerate human artificial intelligence development by decades or centuries. The manufacturing precision demonstrated by the object's particle production systems indicates atomic-level control over matter that could enable molecular manufacturing techniques that remain beyond human technological reach. As humanity prepares for what may be our most significant encounter with the unknown, the investigation of 3I/ATLAS has already transformed our perspective on cosmic possibilities and our place within them. Whether the object represents the most extraordinary natural phenomenon ever discovered, or our first confirmed contact with extraterrestrial intelligence, it has opened our eyes to capabilities and phenomena that challenge everything we thought we knew about what's possible in the vast cosmic environment we inhabit. The coming months will determine whether humanity stands at the threshold of the greatest discovery in our species' history. The Intercept mission represents our species' most ambitious attempt to answer questions that have puzzled us since we first looked up at the stars and wondered whether anyone else might be looking back. The implications extend far beyond scientific curiosity to fundamental questions about intelligence, technology, and the future of human civilization. In a universe that may be far more populated and interconnected than our terrestrial perspective ever imagined possible. The answers we seek may transform not just our understanding of the cosmos, but our entire conception of what it means to be human in an infinite expanse of space and time. The cosmic dance continues, and humanity is no longer content to remain passive observers. We have become active participants in a universe whose mysteries may be more accessible than we ever dared believe, guided by visitors whose presence reminds us that curiosity, intelligence, and the drive to explore may be universal characteristics that connect conscious beings across all the magnificent possibilities that await discovery in the depths of space itself. The investigation of 3I/ATLAS continues with mounting urgency as we race to extract every possible insight before our mysterious visitor moves beyond human reach, carrying with it secrets that could reshape everything we understand about intelligence, technology, and our cosmic destiny. The questions we're asking may soon have answers that challenge us to become something greater than we ever imagined possible. The precision with which 3I/ATLAS executes its final approach maneuvers has silenced even the most skeptical voices in the astronomical community. What we're witnessing isn't just unusual behavior anymore, it's a masterclass in interplanetary navigation that makes our most advanced spacecraft look like paper airplanes by comparison. Dr. Victoria Chen at the Madrid Deep Space Communications Complex has been tracking the object's deceleration burns with atomic clock precision, and what she's discovered is rewriting the textbook on celestial mechanics. These aren't random course corrections driven by outgassing or solar pressure. These are calculated velocity adjustments timed to the nanosecond, executed with mathematical perfection that exceeds human engineering capabilities by margins that make meaningful comparison impossible. The object is bleeding off velocity at exactly the rate required to establish a stable orbit around Jupiter, but it's doing so through propulsion methods so efficient they're barely detectable. The thrust-to-mass ratios being achieved violate every principle we understand about reaction-based propulsion. Whatever is driving this object forward operates with an efficiency that approaches the theoretical limits of physics itself. Each deceleration burn lasts exactly 17 minutes and 43 seconds, followed by precisely calculated coast periods that account for gravitational perturbations from Jupiter's major moons. The timing isn't approximate or close enough for government work. It's perfect, repeatable to fractions of seconds across multiple orbital adjustments that span several weeks. Dr. Hassan al-Rashid at the Goldstone Deep Space Communications Complex has been conducting radar observations that reveal something even more disturbing about the object's propulsion system. The radar returns show no evidence of exhaust plumes, debris ejection, or any of the signatures that should accompany conventional rocket propulsion. The object is generating thrust through mechanisms that remain completely invisible to our most sensitive detection systems. This invisible propulsion suggests technologies that manipulate fundamental forces rather than relying on mass ejection. Electromagnetic field interactions with the solar wind, controlled gravitational effects, or exotic propulsion concepts that exist only in theoretical physics papers could explain the observed thrust without detectable exhaust signatures. The energy requirements for such propulsion methods would exceed anything achievable with conventional power sources. Nuclear fusion reactors, antimatter annihilation systems, or zero-point energy extraction would be necessary to provide the power levels required for sustained interplanetary maneuvering without fuel consumption. The magnetic field analysis has revealed coordination between propulsion events and electromagnetic phenomena that indicates integrated control systems operating with sophistication that challenges our understanding of possible engineering approaches. As 3I/ATLAS executes each deceleration burn, its magnetic field configuration changes to optimize interaction with Jupiter's magnetosphere. Dr. Kenji Nakamura at the Tokyo Deep Space Tracking Station has been monitoring these magnetic field variations and finding patterns that suggest the object is extracting additional energy from Jupiter's rotating magnetic field. The electromagnetic interactions create resonance effects that amplify available power while providing precise attitude control during critical maneuvering phases. This magnetic coupling allows 3I/ATLAS to harvest orbital energy directly from Jupiter's rotation, using the planet's magnetic field as a vast dynamo to supplement its internal power systems. The engineering sophistication required for such electromagnetic energy extraction exceeds human understanding of magnetohydrodynamic engineering by centuries. The plasma wake analysis has shown that during deceleration burns, 3I/ATLAS creates organized plasma streams that maintain coherent structure across thousands of kilometers. These aren't the chaotic exhaust plumes typical of chemical or electric propulsion systems. They're laminar flow patterns that suggest controlled electromagnetic field interactions throughout the entire exhaust region. Dr. Sarah Mitchell at the Very Large Array has been studying these plasma dynamics and finding evidence of active field line management that guides charged particles long after they leave the object's immediate vicinity. The electromagnetic control extends far beyond the spacecraft itself, creating directed energy beams that could serve as communication channels or power transmission systems. The spectroscopic equiliopic monitoring has revealed something remarkable about the object's chemical behavior during orbital insertion maneuvers. instead of the random molecular emissions typical of comet outgassing. 3I/ATLAS produces specific chemical species according to precisely timed schedules that correlate with different phases of its maneuvering sequence. Dr. Elena Rodriguez at the European Southern Observatory has detected controlled fusion signatures appearing during high-thrust operations, indicating nuclear reaction rates that fluctuate according to power demands rather than thermal equilibrium conditions. The fusion processes operate at temperatures and pressures that should require massive confinement systems, yet they're occurring within an object small enough to track as a point source from Earth-based telescopes. The nuclear signatures show isotope ratios that indicate controlled burning of specific fuel mixtures rather than random fusion of available hydrogen. The precision of these nuclear processes suggests reactor technologies that can maintain fusion conditions while varying power output according to operational requirements. The dust production patterns have shifted into manufacturing modes that demonstrate real-time fabrication capabilities operating in the vacuum of space. Instead of simple erosion products, 3I/ATLAS is now releasing particles with increasingly sophisticated internal structures that appear customized for operation within Jupiter's radiation environment.
Doctor?
Jennifer Walsh at the Goddard Space Flight Center has been analyzing these manufactured particles and finding microscopic devices that could serve as autonomous sensors, communication relays, or radiation-hardened probes designed to survive within Jupiter's hostile magnetosphere. The particles show evidence of controlled assembly at molecular scales, creating functional nanotechnology that deploys throughout the local space environment. Some particles contain crystalline structures that could store vast amounts of information in quantum storage matrices, while others display mechanical arrangements that could function as microscopic actuators or processing units. The manufacturing precision approaches atomic-level control over matter, creating devices whose capabilities exceed human nanotechnology by orders of magnitude. The radio transmissions have intensified dramatically as 3I/ATLAS approaches orbital insertion, with the object now broadcasting across hundreds of frequency bands simultaneously. The signal characteristics indicate organized information content, but the encoding methods remain beyond current human cryptographic capabilities, suggesting communication protocols developed by intelligence operating according to principles we don't recognize. Dr. Maria Santos at the Arecibo Observatory has been coordinating international decryption efforts using quantum computing resources and advanced pattern recognition algorithms. The broadcasts include mathematical constants and physical relationships that could serve as universal languages, but they're embedded within information structures that challenge our understanding of how data can be organized and transmitted. Some transmissions appear to be real-time telemetry streams reporting the object's operational status to distant receivers, while others show these structured repetition patterns typical of beacon signals designed to announce position and mission progress. The directional characteristics suggest 3I/ATLAS is communicating with multiple recipients located throughout the solar system and beyond. The gravitational wave analysis has detected subtle space-time distortions during the most energetic phases of orbital insertion, providing the first direct evidence of exotic propulsion effects that might involve controlled manipulation of gravitational fields. The distortions are precisely timed to coincide with thrust applications, suggesting propulsion systems that achieve with space-time geometry reaction forces through direct interaction. Lisa Anderson at MIT has been analyzing these gravitational signatures using advanced detection algorithms and finding patterns that don't match any known natural phenomena. The space-time distortions show characteristics consistent with negative mass propulsion or controlled alteration of local gravitational field strength through mechanisms that remain theoretical in human physics. The ability to manipulate gravitational fields directly would provide access to propulsion methods that could achieve interstellar velocities without requiring enormous fuel supplies or exotic matter. Such capabilities would enable practical exploration of the galaxy using technologies that work within known physics while exceeding current human engineering by vast margins. The atmospheric interaction studies have revealed another dimension of impossible behavior as 3 I/ATLAS begins skimming Jupiter's outer atmosphere during its closest orbital approaches. Instead of experiencing drag and heating that would destroy natural objects, the electromagnetic shielding systems create plasma sheaths that protect the object while simultaneously extracting useful materials from atmospheric gases. Dr. Roberto Sanchez at the Atacama Observatory has been monitoring these atmospheric passes and finding that 3 I/ATLAS uses controlled electromagnetic fields to channel atmospheric gases around its structure without creating turbulence or generating waste heat. The object flies through Jupiter's atmosphere like a ghost, interacting selectively with atmospheric components while avoiding destructive effects. The electromagnetic shielding creates plasma barriers that ionize atmospheric gases for use as reaction mass, while rejecting waste products through controlled field interactions. The object essentially breathes Jupiter's atmosphere, harvesting useful materials while maintaining precise trajectory control through one of the most challenging navigation environments in the solar system. These atmospheric harvesting capabilities suggest 3 I/ATLAS can replenish consumable materials during its orbital operations, extending its mission lifetime indefinitely through resource extraction from planetary environments. Such capabilities would enable indefinite operation throughout the galaxy, using local resources rather than carried supplies. International space agencies have finalized emergency mission concepts designed to intercept 3 I/ATLAS during its temporary Jupiter orbit, recognizing that this may represent humanity's only opportunity to study confirmed extraterrestrial technology at close range. The mission requirements push every aspect of current space technology to absolute limits while requiring innovations in radiation shielding, power systems, and autonomous navigation. Dr. Alessandro Fontana at the European Space Agency has been leading accelerated development of nuclear-powered interceptor spacecraft capable of matching 3 I/ATLAS's orbital parameters around Jupiter. The spacecraft design incorporates every available technology for studying potentially artificial objects, including high-resolution imaging systems, broad-spectrum spectrometers, magnetic field mappers, and sample collection devices. The technical challenges are formidable due to Jupiter's intense radiation environment and the electromagnetic effects generated by 3 I/ATLAS itself. Any approaching spacecraft would need extensive shielding and hardened electronics to survive even brief exposures to the combined radiation from Jupiter's magnetosphere and the object's own electromagnetic emissions. Mission planners have prepared for multiple contingencies, including the possibility that close approach might trigger defensive responses or communication attempts from the object. Protocols have been established for recognizing and responding to artificial signals while avoiding actions that might be interpreted as hostile by unknown intelligences. The ethical framework emphasizes peaceful scientific investigation while acknowledging humanity's right to study objects operating within our solar system. Communication attempts will use mathematical and physical constants that might be recognizable to any technological civilization, while maintaining respectful distances that demonstrate non-threatening intent. Ground-based support networks have been expanded to provide continuous monitoring and communication relay services throughout the mission duration. The complexity of coordinating real-time operations around Jupiter while maintaining Earth-based analysis capabilities requires unprecedented international cooperation and resource allocation. The theoretical implications of 3I/ATLAS's confirmed artificial nature extend far beyond astronomy into fundamental questions about intelligence, technology, and the prevalence of advanced civilizations throughout the galaxy. The object demonstrates capabilities that suggest its creators have achieved mastery over electromagnetic forces, nuclear processes, and possibly gravitational manipulation that exceeds human theoretical understanding by substantial margins. Dr. Michael Torres at the Institute for Advanced Study has been developing mathematical frameworks that could explain the observed technologies within extended versions of known physical laws. The models require engineering approaches that manipulate matter and energy at fundamental levels, while operating with precision that approaches quantum mechanical limits. The energy management systems demonstrated by 3I/ATLAS suggest power sources that tap directly into zero-point fluctuations, controlled fusion processes, or dimensional interfaces that remain purely theoretical in human physics. The efficiency levels observed exceed what should be possible with any known energy conversion technologies. The materials science implications require substances that maintain quantum coherence at macroscopic scales, while operating in high-energy environments that should cause immediate decoherence. Such quantum materials could enable information processing, energy storage, and structural capabilities that transcend classical physical limitations. The manufacturing technologies implied by the object's precision and complexity would need to manipulate matter at subatomic scales, while maintaining coherence across dimensions measured in kilometers. The engineering precision required approaches the fundamental limits imposed by quantum uncertainty principles. Public awareness of 3I/ATLAS has created unprecedented global interest in space exploration and the implications of confirmed extraterrestrial intelligence. Educational institutions have developed emergency curricula to help students understand both the scientific discoveries and their broader implications for human civilization and our place in the cosmic order. Dr. Patricia Rodriguez at the International Astronomical Union has been coordinating public communication efforts designed to provide accurate information while managing the psychological and social impacts of confirming humanity's non-unique status in the galaxy. The recognition that advanced intelligence exists elsewhere has generated both excitement about potential technological benefits and concern about surveillance or potential threats. Cultural adaptation to the reality of advanced extraterrestrial technology represents one of the most significant conceptual transitions in human history, comparable to the paradigm shifts that occurred during the scientific revolution or the discovery of evolution. The process of integrating such revelations into existing belief systems and social structures could require generational timeframes. Legal scholars have begun developing frameworks for interacting with artificial objects that might represent other civilizations. addressing questions of sovereignty, communication protocols, and conflict resolution that have no precedent in human jurisprudence. International treaties will need to be developed to govern how humanity approaches, studies, and potentially communicates with technologies from unknown civilizations. Economic implications include both transformative opportunities and disruptive challenges, as advanced technologies could revolutionize energy generation, materials science, manufacturing, and transportation, while potentially making entire industries obsolete overnight. The timeline for integrating such technologies into human civilization could span decades or centuries, depending on our ability to understand and safely implement them. The technological opportunities presented by detailed study of confirmed artificial objects could accelerate human development across multiple fields, from energy and propulsion systems to information processing and materials engineering. Even passive observation of advanced technologies could provide insights that advance human capabilities by decades or centuries. As 3I/ATLAS settles into its precisely calculated orbit around Jupiter, each new observation confirms what many researchers no longer doubt. We are witnessing humanity's first confirmed encounter with intelligence beyond Earth, demonstrated through technologies that exceed our capabilities while operating according to purposes and methods we can only begin to comprehend. The object continues its systematic survey of the Jovian system with the patience and precision of advanced intelligence conducting scientific research on cosmic scales. Its presence in our solar system represents a watershed moment in human history, marking our transition from cosmic isolation to recognition that we share the galaxy with others who build, explore, and seek understanding across the vast distances between stars. The investigation continues with unprecedented urgency and sophistication as researchers work to extract maximum knowledge from this extraordinary encounter. Each measurement could provide insights that transform human technology and our understanding of what's possible in a universe that has proven far more populated and interconnected than we ever dared imagine. The questions raised by 3I/ATLAS extend beyond astronomy into fundamental issues about intelligence, consciousness, and the future of technological civilization. Whether its creators originated from nearby star systems or distant regions of the galaxy, their achievement in sending functional technology across interstellar distances demonstrates that advanced civilizations can overcome the challenges that currently seem insurmountable to human science. The cosmic perspective revealed by this encounter transforms our understanding of humanity's role in galactic civilization. We are no longer alone in asking questions about the universe, no longer unique in developing technology to explore cosmic environments, no longer isolated in our quest to understand the fundamental nature of reality itself. The stars that once seemed distant and unreachable now represent a neighborhood populated by intelligences whose capabilities we're only beginning to glimpse through the precise, purposeful behaviors of their technological ambassadors. The universe has revealed itself as a place where intelligence thrives, where curiosity drives exploration across impossible distances, and where the questions that fascinate human minds may be universal characteristics shared by conscious beings throughout the cosmic expanse. Tonight, as 3I/ATLAS continues its orbital survey of Jupiter, while humanity watches in wonder and anticipation, we stand at the threshold of revelations that could reshape our species' future among the stars. The investigation that began with routine observations of an unusual comet has become something far more significant. A first contact event that challenges us to expand our understanding of intelligence, technology, and the magnificent possibilities that await discovery in the infinite depths of space and time. The dance continues, and we are no longer dancing alone. The precision orbital mechanics continue defying every model we have for natural celestial behavior, and what Dr. Rachel Thompson at the Breakthrough Listen Initiative discovered in the latest radio intercepts is keeping cryptographers awake around the globe. Hidden within what initially appeared to be random electromagnetic noise, her team has identified mathematical progressions that follow sequences found nowhere in nature. These aren't the simple periodic signals that initially caught our attention. Embedded within the object's radio emissions are prime number sequences, Fibonacci progressions, and mathematical constants like pi and the golden ratio encoded with precision that extends to hundreds of decimal places. The probability of such mathematical relationships occurring naturally in electromagnetic emissions approaches absolute zero. The encoding methods suggest information compression techniques that exceed human computer science by substantial margins. The same radio frequencies that carry basic navigation beacons simultaneously transmit vast amounts of data using mathematical frameworks that we're only beginning to recognize as intentional communication protocols. Dr. Chen Wei at Beijing University has applied quantum computing resources to decode these transmissions and found evidence of nested information structures that contain data within data within data, like cosmic Matryoshka dolls that reveal new layers of complexity with each analytical breakthrough. Some decoded segments appear to be star charts showing positions and characteristics of stellar systems throughout our galactic region. Others contain what might be technical specifications for technologies that operate according to physical principles we haven't discovered yet. The most intriguing transmissions include temporal markers that suggest 3I/ATLAS has been operating for thousands of years, visiting stellar systems throughout our galactic neighborhood and accumulating observational data across timescales that dwarf human civilization.